All right, so the first question on our quiz is, a stationary wave is formed on a stretched string. The diagram illustrates the string at an instant of time when the displacement of the string is at its maximum. So this part of the string is at its maximum displacement. The amplitude, right, is the maximum displacement. Here we see point P at the maximum displacement below equilibrium. It says the frequency of the wave is 250 hertz. Point P on the string has a vertical displacement of -1 millimeter. So that's -1 millimeter below this point. What will be the vertical displacement of the point P after a time of 5 milliseconds? So we have to relate sort of the frequency to the time period. If we know the frequency of a wave, we can immediately calculate the time that it takes to oscillate, because you may recall that frequency is equal to 1 over t. So t would then be 1 over the frequency, and 1 over 250 is what? 1 divided by 250 equals 0.004 seconds. And so we could even write that as 4 by 10 to the -3, or we could say 4 by 10 to the -3 seconds is the same thing as 4 milliseconds. So this wave has a time period of 4 milliseconds. We want to know where point P is going to be after 5 milliseconds. It'd be nice if this said 4, right? Because then we would just say, well, if that's the time period, what does time period mean? It's the amount of time per wave, per oscillation. So this point is going to move up to equilibrium, move to this point up here, maximum displacement above equilibrium, back down to where it started after 4 milliseconds. So I think it's helpful to sort of break down its oscillation into quarter cycles. Remember, we talked about the phase of the wave, and we could say you could break it down into 360 divisions, degrees, or 2 pi radians, or quarter cycles. So if we think about quarter cycles, it would be 1 millisecond would be a fourth of this, and so after 1 millisecond, it would be here, back to equilibrium. After 2 milliseconds, it's going to be here at sort of maximum displacement. So we go 1 millisecond, 2 millisecond, 3 milliseconds, 4, right? And you just kind of count it out like that. Isn't that a nice way to solve it? So if you think through it like this, probably everybody by now knows the answer, even though we haven't really calculated it. And so if that's the way to get to the answer, go for it. Choose your best answer now, or make a correction before I tell you the answer. Okay. 1 millisecond, 2 milliseconds, 3 milliseconds, 4 milliseconds. I want to know after 5 milliseconds. So that's going to be right back up to here, 0 displacement, right? It's going to be on its equilibrium line. So 1 millisecond after this, all of these points, like all these points are moving up, right? All these points are moving down. That's why we said adjacent loops are out of phase. They're 180 degrees out of phase, because all these particles move up while all these particles move down. After 1 millisecond, what's this going to look like? They're all going to be right there. You're going to be able to see that it's a standing wave because this thing is going. And you got to use sound effects. Let your eyes adjust. Got to use sound effects to appreciate it, guys.